Hello dear friends, welcome to the lecture of number theory. In this lecture we shall study some multiple choice questions on number theory which are on the topics that we have studied: divisibility of integers, then primes and their distribution, theory of congruences, number theoretic function, Fermat's theorem, and Euler's generalization of Fermat's theorem. So on these topics we shall study the multiple choice questions. To study a multiple choice question, we have to study the content first. The definitions, results and some simple problems must be studied first, and then we can attempt these multiple choice questions. I will suggest you to pause this video, take a screenshot of this and attempt these questions, note down your answers and then verify the answers. Now we will consider these questions one by one. The first is, if two integers a and b, not both 0, are relatively prime, then which is the correct alternative? The relatively prime integers, LCM of a and b is equal to 1. Second, GCD of a and b is 1. LCM of a and b is equal to 0, and GCD of a and b is equal to 0. So which is the correct alternative? So by definition of relatively prime integers, we mean their GCD is 1. So greatest common divisor of two integers is 1, then the two integers are said to be relatively prime. So therefore this is the correct alternative, that is B is the correct. For example, 3 and 5 are relatively prime because their GCD of 3 and 5 is 1, and therefore this is an example of relatively prime integers. So this is actually the definition. If the GCD is 1, then the two integers, GCD of the two integers is 1, then the two integers are relatively prime. The second one is A divides B into C and GCD of A and B is 1, then which of the alternative is correct? Then A divides B, second is B divides A, third is A divides C, and the last is C divides A. Now here A divides B into C, but A does not divide B because the GCD of A and B is 1. So therefore A must divide C, and that means the third alternative is correct. A divides C. The next is, if A is equal to QB plus R, then the GCD of A and B, GCD of these two integers is equal to which number? Is equal to 1, or GCD of A and Q, and the next is a GCD of A and R, GCD of B and R. So for this we can have the GCD of A and B, it may be 1, and therefore instead of this alternative we will consider this as GCD of A. We have taken GCD of A and Q, GCD of one more we will consider GCD of Q and B. Instead of 1 I shall write this is GCD of QB. Q and B. This is actually a result on Euclidean algorithm to find the greatest common divisor, and therefore if this is divisibility division algorithm is used for A and B. Q is quotient and R is remainder. A is divided by B, A is equal to QB plus R, then GCD of A and B is equal to the GCD of B and R. So and so on, this chain of division continues and we get the greatest common divisor. So therefore GCD of these two integers A and B is equal to GCD of the integer B and R, and this is the correct alternative. Next is, for any two positive integers A and B, if GCD of A and B is 6 and LCM of A and B is 60, then what about the product A into B? Actually, the product A into B or absolute value of the product, these are positive integers, therefore this will be positive. A into B is equal to the product of GCD and LCM. So therefore this is actually GCD, AB is equal to GCD of AB into LCM of AB, and therefore this will be, what is GCD is given as 6 and LCM is given as 60, 6 into 60, that is 360, and therefore this is the correct alternative. Next is, if A is given as 119, B is 272, then greatest common divisor of A and B is one of these, 17, etc. Here we have to use the Euclidean algorithm, and for that purpose we will do the work here. B is 272 and that is the greater, and this is smaller. So greater number 272 is to be divided by smaller number, and that is 119. See, the quotient is 2. We will write the quotient here, and then 119 multiplied by 2 is 238. The subtraction gives 34, and again we take this number here, that is 119, and perform the same procedure of the division. So here the quotient will be see, it will be 3, and then the product of 34 into 3 is 102, and the subtraction is 17. Again we take 34 here and divide 34 by 17. The quotient is 2, and now the remainder is 0. In this process of, this is the process of Euclidean algorithm. The greater number is divided by smaller number, and again we take this first number here, which is divisor, first divisor here, and divide by 34, and so on. In this process the remainders are 34, 17 and 0. The last non-zero remainder, last non-zero, this is the 0 remainder, but last non-zero is 17, and therefore this is the GCD of the two numbers, and that therefore the answer is 17. Sixth question is, which of the following is not correct? That is 3 is congruent to 24 under modulus 7. Here we have to only use the definition of congruence. So what is the definition of congruence? We say A is congruent to B modulo n. A congruent to B modulo n if, or this implies and implied by, n divides A minus B. This is the definition of congruence, and we check this, we shall check this definition, and then we will decide which is not correct here. So that means this 7, n is here 7, and this must divide the difference of these two, 3 and 24. The difference of 3 and 24 taken in 3 minus 24 as minus 21, and 7 divides obviously minus 21. So this is correct. Here what is the difference of 31 and 11? Minus 31 and minus 11. The difference is minus 42. 7 also divides for minus 42, and this is the difference of minus 15 and minus 64, means minus of minus 64, that will be plus 64, and therefore it can be considered as 64 minus 15, and see, the difference is 49, and 7 divides 49. So therefore this is also correct. What about the last? The difference of 25 and 12. 25 and 12 is 13, and 7 does not divide 13. That means 7 does not divide the difference of 25 minus 12, and therefore this is not correct. The last is not correct is us, so last is not correct. Next, P P is prime and P does not divide A, then A to the power P minus 1 is congruent to which number under modulo P? So actually the seventh is theorem, Fermat's theorem, and it is, if P is prime and P does not divide A, then A to the power P minus 1 is congruent to 1 under modulo P. So this is a theorem and which is known as Fermat's theorem. So therefore the correct alternative is C. If n is equal to 180, then tau n. These are number theoretic functions, tau, sigma, phi. So what is a tau function? We will define as, for if, see this is for 8 and 9, we will consider the numbers as, if n is equal to canonical form, we will have, if n is equal to p1 power k1, p2 power k2 and so on, pr power kr, where p1, p2, pr are primes and k1, k2 etc. are non-negative. Then tau n is k1 plus 1, this index of p1, k1 plus 1, k2 plus 1 and so on, kr plus 1. This is the expression for tau. And sigma of n will be equal to, now if you consider these numbers, then that can be defined in the form of p1 to the power k1 plus 1 minus 1 divided by p1 minus 1 and so on, p2 to the power k2 plus 1 minus 1 divided by p2 minus 1, and last will be pr to the power kr plus 1 minus 1 divided by pr minus 1. So this is sigma of n. And one more is phi function, Euler's phi function. Phi function is defined as, actually here what is the meaning of tau n means number of positive divisors less than or equal to n. Say the number of positive divisors of n will be the meaning of tau n, and sigma n is sum of these positive divisors of n. So, and what about phi n? Phi n is also known as Euler's phi function, and this is the number of positive integers that less than or equal to n that are relatively prime to n, and the expression for this is n into, with the help of this expression, n into 1 minus 1 upon p and so on, 1 minus p1, 1 minus 1 upon p1 and so on, 1 minus 1 upon the last is pr. This is the expression for phi, Euler's phi function. Or if you, yes, so these are the numbers we have considered. The number theoretic functions we have written. Tau function, it is number of positive divisors of n and sum of these divisors, and here number of integers, positive integers less than or equal to n and that are relatively prime to n. So that is the meaning. Now what about if you consider tau n, that is tau 12, then this means the number of positive divisors of 12, and that will be 1 is divisor of every integer, so 1 will be always there. So this is 1, then 2, 3, 4, 5 is not divisor of 12, 6 is divisor of 12, and further 7, 8, 9, 10, 11 are not divisors, but 12 is also divisor. So these are the number of positive divisors of 12, and this we have to count it 1, 2, 3, 4, 5, 6, and that means tau 12 is equal to 6. But without considering this, actually finding the divisors, we can use this formula. Now we will use see for this n is there, but tau of 12 can be obtained using this. Now how to write 12? 12 can be written as 2 to the power 2, 3 to the power 1 in this canonical form, p1 power k1, p2 power k2, and therefore by this tau n, that is tau 12 is equal to k1 plus 1, and k1 is 2, k2 is 1. You see, compare it. So 2 plus 1 and here 1 plus 1, k2 is 1, powers are k1 and k2, and therefore it is 3 into 2, that is 6, so which is the same. So thus we can actually find out the numbers. But if it is small, then it is easy, but if the number is bigger, then it will be convenient to use this formula. And what will be sigma of n? Sigma of n is sum of these divisors, that is 1 plus 2 plus 3 etc., and that can be obtained by this formula. Sigma of n, we are going to find it here, and therefore first we shall see what is the tau of n. N is 180, and for that purpose we shall consider n is equal to 180. So 180 can be written in canonical form as, so this is a specific for 8th, n is equal to 180, and 180 is 2 into 9 into 10, or that can be considered as 2 into 9 is 3 into 3 and 10 is 2 into 5, or actually this is to be written as 2 square into 3 square into 5 to the power 1. So 4 into 9 into 5, yes, that is right. And now that is p1 is 2, k1 is 1, k1 is 2, p1 is 2, k1 is 2, p2 is 3, k2 is 2, and p3 is 5, k3 is 1, and from this we can write tau n is equal to that is k1 plus 1. What is k1? These are the powers, these powers are k1, k2, k3, and therefore it will be 2 plus 1, this is 2 plus 1 and 1 plus 1, k1 plus 1 into k2 plus 1 into k3 plus 1, and that number is 3 into 3 into 2, or which will be 18, and thus 18 is the correct answer here for 8th problem. Now if n is 12, what is sigma of n? For sigma n we shall use this formula. For ninth problem, n sigma of n, that is sigma of 12. Sigma of 12 can be, but 12 is to be written first in canonical form. 12 is equal to 3 into 4, 2 square into 3 power 1, 4 into 3. These are prime factorization, and this form is known, p1, p2, pr are primes. This form is known as canonical form. And after writing this first form, then we should use these formulae. Now we want sigma. So what will be sigma 12? This is p1 to the power k1 plus 1. What is p1? That is 2. And 2 to the power k1 plus 1. That is 2 power k1 is 2, 2 plus 1. See, minus 1 divided by again 2 minus 1 into. Next is p2. P2 is 3. 3 power, what is k2? K2 is 1. 1 plus 1 minus 1 divided by 3 minus 1, or actually this will be equal to, this is 2 cube. 2 cube is 8, 8 minus 1 is 7, 7 divided by 1, and this is 9, 3 square is 9, minus 1 is 8, and this divided by 2. So 7 into 4, that is 28, and therefore the answer for 9th is 28. Now what is Phi function? Euler's Phi function. This formula is to be used. that means number of integers that are relatively prime to n, less than or equal to n, and that is 30. 30 can be written in canonical form. 30 is equal to 6 into 5, and 6 is 2 into 3 into 5. So, each has power 1. K1 is 1, K2 is 1, K3 is 1. P1 is 2, P2 is 3, P3 is 5, and therefore, phi n is phi 30 is equal to n. N is again 30 into 1 minus P1 is 2, 1 minus 1 half. This is 1 minus 1 third. 1 minus 1 by P1, 1 minus 1 by P2, etc., and 1 minus 1 by 5, or therefore, this will be 30. And what is the number? This is half. 30 into half. This is 3 minus 1, 2 third, and this is 5 minus 1, 4 by 5. So, actually this 2 into 3 is 6 into 5 cancels with this 30, and the product is 1 into 2 into 4, that is 8, and therefore, the answer is here 8. So, thus these are the important number theoretic function. You should remember these as the formulae for this: tau function, sigma function, and Euler's phi function. So, we will consider the next questions now. I have written next questions. I would suggest you to take a screenshot of this and write your answers first on a paper, and then verify these answers. 11th question is LCM of 12 and 30 is which number? And to find LCM of two numbers, it will be useful to first find the greatest common divisor of the two numbers, and then we can use the relation between LCM and GCD. So, we know that this LCM into GCD is equal to product of the two numbers A and B. Here what will be GCD of 12 and 30 is 6, and therefore, LCM will be is A into B, or that is 12 into 30 divided by 6, or this will be 2 into 30, which is 60. So, this relation is used here, and therefore, the answer is D. Next is number of mutually incongruent solutions of this congruence. 18x congruent to 30 modulo 42 is which of this? This is a linear congruence. It's a linear congruence which is Ax congruent to B under modulo n, and we have the result for this. Ax congruent to B modulo n has solution if D divides n. This is a theorem we have proved, D divides n, where D is the GCD of A and n. And here you see what is A and n. A is 18 and n is 42. So, therefore, this is GCD of 18 and 42, or which we know is 6 into 3 and 6 into 7. So, GCD is 6, and this 6 divides 30, therefore, it has a solution. So, D divides n is 42. So, 6 divides 42, and further it has D number of incongruent solutions. It has D solutions, and that is equal to what is D? D is 6 solutions. So, therefore, this number of mutually incongruent, the solutions must be incongruent to each other under modulo n, and the answer is the first 6 solutions mutually incongruent. So, this is important result relating to linear congruence that we have to remember. Further, if P and Q are distinct primes with A power P is congruent to A modulo Q
and a power q is congruent to a modulo p. See here, power is p, modulo is q. Power is q, modulo is p, interchange of this, and p and q are primes. Then the taking the actually the product of the left numbers, a to the power p into q, not product but power is taken as pq. A power pq is congruent to a under which modulo? So this is a result that we have studied after Fermat's theorem, and the modulo here becomes p into q. So therefore the correct alternative is p into q, that is C. Or this means the result here is a power pq is congruent to a modulo pq if these two congruences are given. This question is exactly dependent on the 13th result. See here, a 2 power 11 is congruent to 2 modulo 31 and 2 power 31 is congruent to 2 modulo 11. Here p is 11, q is 31, and then which of the following is true? So that means this type of result must hold. A power p into q, that is 11 into 31, is congruent to a is 2 and modulo pq 11 into 31, and other congruences are given, but see the first is exactly similar to this result, and therefore this is the correct alternative. Next is if p is prime, then mu of p is equal to which number? Mu is Mobius function. Number theoretic functions, earlier we have seen tau, sigma and phi function. Similarly, there is a Mobius function mu, and that is defined as like this. Mu is equal to, it has a mu of n, actually n is positive integer, mu of n is 1 if n is equal to 1, and mu of n is 0 if p square divides n for some prime p, and this is equal to minus 1 power r if p is equal to, p is written as p1 p2 pr, not p but n, this number n is written as product of p1 p2 up to pr, distinct prime, where pi are distinct primes. So thus this is the result to be remembered about mu of number n, and see if p is prime, then which result will hold here? So p is prime, then p can be taken as p is equal to p itself, prime factorization, and therefore this result can be used. N is prime, product of primes, n is single prime. Suppose 7 is there, then 7 we can write is equal to 7, in n is 7, and therefore it will be minus 1 power r, number of factors, only one factor is there, and therefore if we consider n of mu of 7, then that mu of 7 will be equal to minus 1 power 1, that is minus 1. Or if you consider other, say if I write n is equal to 15, mu of 15 we want to find, and 15 can be written as in terms of prime factors 3 into 5, but there are two factors, therefore this will be minus 1 power r, that is r is 2, this is p1, this is p2, and therefore it will be 1. So like this we can find out the number mu. Or if you consider mu of 4, n is equal to 4, then this 4 is divisible by 2 square. 2 square divides 4. So 2 is prime, and therefore mu of 4 will be equal to 0 by this. See. Or if you consider 9, then 3 square divides 9, or 27, mu of 27 if you consider. 27 is divisible by 3 square. 3 is prime, and therefore this mu of 27 will be 0 by second condition. In this way we can find the number mu or the function mu for a number n, and for prime it is certainly -1, because prime has only one factor, and therefore r is 1, so -1 power 1 is -1. This is the correct alternative. Next is, if p is prime, then which is true? P is prime, which is true. This is factorial of p minus 1 is congruent to 0 mod p. Factorial of p minus 1 plus 1 congruent to 0 modulo p, etc. And this is a theorem which is known as Wilson's theorem. If p is prime, then p minus 1 factorial is congruent to -1 modulo p. But you see, this result exactly does not appear here. But if you can add 1 on both sides, then this will be equivalent to p minus 1 factorial plus 1 is congruent to -1 plus 1 0 under modulo p, and therefore the correct alternative is this one, p minus 1 factorial plus 1 congruent to 0 modulo p. Next is this linear congruence, ax congruent to b modulo n has unique solution if. Now we have seen it has a solution if d is the GCD of a and n divides b. Unique solution for and d number of solutions. So it will have unique solution if GCD of a and n is 1. So GCD of a and n is equal to 1, and that is to be considered as d. So 1 always divides every integer, therefore it has solution certainly, and there is only one solution because d is equal to 1. D number of solutions will be there, and thus the correct alternative for this is a result for linear congruences that we have to remember. The correct alternative is GCD of a and n is 1. Next is, if CA is congruent to CB modulo n, then A is congruent to B modulo n by d is true only if. So what about D? D is here. What is to be considered as D? D is again GCD of C and n. C can be cancelled, but in the cancellation on both sides we will get the congruence A congruent to B, but the modulo will change. The modulo will be n divided by d. And what is the d? D is the GCD of C and n. So this is also a result we have studied earlier in theory of congruences, and thus the value of d must be GCD of C and n. So this is the alternative correct. And next is, the GCD of A and B is d, then GCD of A divided by d and B divided by d will be which number? Because GCD of A and B is d, if you divide A by d and B by d, they will be relatively prime. They will become relatively prime, and therefore their GCD is 1. So this is also a result that we have studied in the first chapter, divisibility. So thus we have discussed these questions. Now we consider the next questions. Now these are the next questions. I will suggest you to take screenshot of this and write the answers, then verify. The 20th question is, GCD of -8 and -36 is which number? See, GCD of positive or negative number, whatever it may be, GCD is always positive, and therefore greatest common divisor it is, and therefore it is always positive. It's a simple question, and we know the GCD of 8 and 36 is 4, and therefore the GCD of minus 8 and minus 36 is also 4. GCD of minus 8 and plus 36 will be the same, or the result is GCD of A and minus B, GCD of minus A and minus B, or GCD of minus A B is same as GCD of A and B. All are equal, and therefore the GCD of minus 8 and minus 36 is 4 only. Next is the linear Diophantine equation. Ax plus by equal to c has solution if D divides C. This is the condition, or actually this is the theorem for existence of solution of Diophantine equation. If D divides C, where what is the D? D is the GCD of A and B here, and therefore this is actually a theorem, and the value of D is GCD of A and B. And again the next question is related to the same Diophantine equation. The Diophantine equation 5x plus 22y is equal to 18. Now we compare, here A is 5, B is 22 and C is 18. Has one solution is given, but has a solution whether this condition is satisfied, D divides C. What is D? D is the GCD of 5 and 22, which is 1, and 1 always divides every integer, so therefore the solution exists. And now further, if one solution is given by x naught y naught, then what about the other solutions? So that is given in the same theorem. So if one solution is D divides C, then it has a solution, and if one solution is x naught y naught, then the other solutions are x is equal to x naught or congruent to x naught plus b by d times t modulo n, and further y is equal to y naught minus a by d times t. These are the other solutions that are given. And now here what is x naught? X naught is 8, y naught is minus 1, and what is d? D is the GCD of C 5 and 22, and so actually this is x is equal to x naught plus b by d, t is arbitrary, GCD of 5 and 22, this is 1, and therefore other solutions will be given by x is equal to x naught is 8 given here, plus b is this number, this is a and this is b and this is c. So b by d is 1, so it will be 22 times t, and y is equal to y naught is minus 1, and minus it is minus a is 5. So all solutions will be given by this relation, x is equal to 8 plus 22t, y is minus 1 minus 5, and therefore the answer we can see is here D is the correct answer. Further, 35x is congruent to 1 modulo 3. This congruence has a solution. Which of this is a solution? And that is easy to solve the congruence. 35 congruent to 1 under modulo 3. 35x congruent to 1 modulo 3. Now, but 35 is congruent to which number under modulo 3? So, we divide 35 by 3, the remainder is 2 under modulo 3, and therefore this congruence will reduce to as 2x is congruent to 1 modulo 3. And now we can check the solutions among this easily. So, whether 8 is congruent to 1 under modulo 3? No. and x is 1, that is 2. 2 is congruent to, how to check it? 3 must divide the difference of 2x minus 1, and you put the values of x. 3 divides 8 minus 1, 7. No. X is 1, that is 2 minus 1. 3 does not divide 1, and x is 3. 3 into 2, 6. 6 minus 1, that is 5. 3 does not divide 5. X is 2. 2 into 2, 4. 4 minus 1 is 3. 3 divides 3, and therefore this is the correct alternative, D. Next is, if n minus 1 factorial is congruent to minus 1 modulo n, then what is the value of n? Again, this is the Wilson's theorem. Actually, the theorem is, if p is prime, then p minus 1 factorial is congruent to minus 1 modulo p. P is prime, and therefore this relation is satisfied by a prime number, and we can see the prime here is 13, and therefore C is the correct alternative for this question. Next one is, if n is greater than 0, then tau n, this is a number theoretic function, we have seen earlier also. Tau n is which of positive divisors, or dot dot of positive divisors of n. So we have to put one word here so that the statement becomes true. So tau n is the product of positive divisors of n. If you put here product, then whether it is product of positive divisors of n, or it is sum of positive divisors of n, or difference of positive divisors of n, or number of positive divisors of n. By definition, tau n is number of positive divisors of n, and therefore this is the correct alternative. Next is, a number theoretic function f is said to be multiplicative whenever GCD of m and n is 1, they are relatively prime, and if, which result must hold? By definition of number theoretic function as multiplicative function. Multiplicative function, we have f of m into n is equal to one of this, product or sum or difference or quotient, and it is multiplicative, therefore the first is the correct choice. F of m into n is equal to f of m into f of n. And the next one, if p is prime, k is greater than 0, then phi of p power k, phi is Euler's function, phi, and we have the result phi of n is equal to, if n has the prime factorization, as p1 or p2 etc. PR, and these are distinct, then phi of n is equal to n into 1 minus 1 upon p1, 1 minus 1 upon p2 etc., 1 minus 1 upon PR, and here phi of p power k will be equal to n is p power k, and this is 1 minus 1 upon p only, because it has only one factor, p power k. If it may be considered as p power k1, p power k2, p power pr power kr, and then it will have this expression. So thus, but this result is, if you multiply by p power k inside the bracket, it is p power k minus p power k divided by p means p power k minus 1. So this is the result for Euler's phi function to be remembered, and then you can see the correct alternative is second, B. B is the correct alternative. The next one is the value of sigma mu of D is which one? Mu is Mobius function, we have defined earlier in earlier multiple choice question, you should refer that, but one theorem is about mu or summation of this mu of D, and this is equal to 1 if n is 1, and 0 if n is greater than 1. Positive integers these are, and therefore here you see n is 10 which is greater than 1, and therefore summation d divides 10 mu of d will be here 0. Then this can be easily verified by considering mu number for this by definition of mu. So this is actually a result or a theorem, and using this we can easily write the sigma mu of d divides n. So because 10 is greater than 1, the resulting number is 0. So thus we have solved some multiple choice questions on number theory. So thank you for watching the lecture.